For the next limit, we have the limit of the square root of x squared minus x minus x. So if we attempt direct substitution here, what we see happening is we have infinity squared minus infinity. So this is going to be infinity, and the square root of infinity is infinity, minus infinity. So this is another indeterminate form, and it's actually called the indeterminate difference. What you 100% cannot say is that this means it's zero. And the reason you can't conclude that is because we have two completely different kind of forms of infinity going on. There's no way to really distinguish between. We just know their numbers so incredibly large that they round up to infinity. So you actually don't know. This could be way, way bigger than this. This could be bigger than this. So this is actually an indeterminate form. Now, typically when this happens, the first thing that you want to hope for is that you maybe have some fractions and you want to get a common denominator and then take another look at it. But in this situation, we don't have that option. So when you see a radical, that's a red flag to say, well, maybe I can try using the conjugate. And what the conjugate allows us to do is it allows us to square this radical legally in math. Now, you can't just arbitrarily square it, because when you square something, you have to have the other side of an equation to also square. So let's try multiplying this by its conjugate. And the conjugate is, if this is some a minus b, the conjugate is you take that first thing and then plus the second thing. So you're getting an a minus b times an a plus b situation. But to make this a legal move, we must also do this to the denominator. So this becomes just a really funky looking 1, right? And anything times 1 is itself. Now, when we use the conjugate in the numerator, right, you heard me say a minus b times a plus b, there's no really need to FOIL this, because when we multiply conjugates, it's the difference of squares. So this multiplies out to be a squared, which is just x squared minus x, makes the radical go away, minus x squared. And the denominator is still just along for the ride. Now, if I clean up the numerator, x squared minus x squared simply gives me negative x in the numerator. And if we were to attempt direct substitution here, it would give us infinity over infinity, which it would be very, very tempting to try L'Hopital. But I would pause on that because of this radical. So remember, the whole goal of L'Hopital is to keep taking derivatives until we can distinguish between the numerator and the denominator. But the derivatives of this are going to get like increasingly disgustingly nasty. So we might actually be able to find an algebraic solution out of this. So if I look at this a little bit further, I see here that if I had the ability to maybe cancel this x in some way, then that would eliminate my infinity problem in the numerator. And if I look in the denominator, I have an x here. So if I could somehow find an x here, right, I could potentially factor it out. So the highest power of x in the numerator is x to the 1. The highest power of x in the denominator is also x to the 1, because even though you see an x squared here, this guy's sitting under a radical. So the square root of x squared is either going to be negative x or x. Since we're in positive territory, it's going to be x. So what I'm going to do is something similar to when we were dealing with polynomials, is if I multiply the numerator by 1 over x, I want to also multiply the denominator by 1 over x. But if I'm thinking in terms of my radical here, what I'm actually going to do is multiply the denominator by the square root of 1 over x squared. Now, you can see here, because x is positive, going to positive infinity, the square root of this is in fact 1 over x. So this is just a unusual looking 1 here. So now let's distribute across the numerator. So negative x times 1 over x is simply going to give me negative 1 in the numerator. Now let's distribute across this denominator. So I'm going to deal with the radical first. So 1 over x squared times x squared is going to give me 1. X times 1 over x squared is going to give me 1 over x. And then remember how we said this is just a 1 over x all along? Well, 1 over x times x is simply going to give me 1. So now let's try direct substitution. And we get negative 1 in the numerator. I get 1 minus 0 in the denominator because the limit as x goes to infinity of 1 over x is 0. So I get the square root of 1. And then we have our plus 1. So this works out to be negative 1/2 because this is just 1 plus 1 is 2. So negative 1/2 is the answer to this limit.